All right, section 8.2, we're going to be looking at a topic called integration by parts. We're just going to start it. But integration by parts comes from the product rule. So I want you to think about this is one version anyway of the product rule. The product rule says that if I want the derivative of a product, u times v, I leave one piece the same. I always write mine as the first piece, u, and I do the derivative of v, which we call v prime a lot of times, and then I reverse the order. So then I do plus v times the derivative of u. Now, if we sort of undo this and we integrate each of these pieces like this, the integration and the derivative of the first piece cancel out. Make sense? And I'm left with uv. That's what happens down here on my next line. The v prime is the derivative of v, and I'm just going to write it as dv. It's just another way to write it. We don't usually write it that way, but for the purposes of the way this is defined, I'm going to change the notation. And the same thing on the other one. The u prime is written as du. Okay, so integration by parts is kind of like the opposite of, or the inverse of, the product rule. And this is exactly what our definition looks like for integration by parts. Integration by parts, theorem 8.1 says, if u and v are functions of x with continuous derivatives, then I'm going to change this. I'm going to move some things around with a little bit of algebra. I'm going to take this piece and I'm going to subtract it to the other side. So the integral of u dv, which is where I'm starting here, is equal to uv minus the integral of v du. Okay, just algebra, simplification, solving an equation. Okay, so that's fine. We can sort of visualize that we're shifting some things around with algebra. But what we want to know, and what you probably want to know then, is how do I really do it though, right? Like what does that mean I actually have to do when I'm given a problem like this? So that's what the rest of this is going to show you. But this is where it comes from. It comes from the product rule, okay? So here's some guidelines for figuring out what, here I should say this too. What we're going to be trying to decide is what u and dv are. So when we're going to be given something that looks like this. It's going to be given as an antiderivative of something that we can't do with some other method. It's not possible. I need to figure out what is my u and what is my dv. And of course, it's not always just super obvious. So this is some guidelines for choosing what do I let be u, kind of like when I do u substitution, what do I let u be, right? And what do I let be dv? So we usually let dv be the most complicated part that fits the integrand of a basic integration rule. Jot it down. I'll show you how it works, I promise. And we want to let u, in general, be a function that becomes simpler as derivatives are taken. For example, some derivatives, some functions are nicer as you take the derivative. For example, if you had x to the fifth and you take its derivative, it becomes 5x to the fourth. If the power goes down, right? It becomes a simpler function. But some functions don't do that. If you have 1 over x and you take its antiderivative, it becomes negative 1 over x squared. That's messier than it started with. Are y'all with me? So some functions have this ability that when you take the derivative, it's sort of nicer, and some become messier, and some just sort of change, like sine. Sine becomes cosine, and then cosine becomes negative sine, and it just has this cyclic, like it never ends kind of thing. And we'll see what happens when this never-ending process happens, because there is an end. It's just not super intuitive as to what happens. So in general, we're trying to let v be the most complicated part and u be the thing that becomes simpler. So we're going to do an example and you're going to see how it works. Are you ready? Here's our first example. So I have x cubed natural log of x dx. And without a doubt, this looks like a product, right? And we do not have a product rule per se for antiderivatives, right? Product rule exists for derivatives, not for antiderivatives. So what we're going to be doing is we're going to be identifying what would we let u be and what would we let dv be? Actually, I'm not write it here. Let me write it over here. What do we let u be and what do we let dv be? Okay, I'm going to model my notes. They're going to be awkward angles. All right, so they're off-centered, and that's what I meant to do. Okay, so we want to let u be something that gets simpler. Well, x cubed gets simpler if I take a derivative, so that's sort of a contender here. But so does natural log of x. And in fact, you do not have a form for what is the antiderivative of natural log of x, correct? Look on your sheet, right? Your antiderivative sheet. There's no antiderivative form for natural log of x. Okay, we're going to talk about what we do with it, but we don't have an antiderivative for natural log of x written down for us yet. What that means is that I can't let the natural log of x piece go down here with the dv, because what I'm going to do is I'm going to take its antiderivative. So whatever I let u be, I'm going to take the derivative, and whatever I let dv be, I'm going to take the antiderivative. Okay, so here's the way this works. We're going to let u be the natural log of x. And in general, anytime you have the natural log of x, it has to be the u part, because we don't have the closed form for the antiderivative of it. And the other piece, so that's this piece, it's now here. The other pieces, I should say, are going to fit down here with dv. So this becomes the integral of u times dv. The u is the part that's in red. Maybe I should write it in red just so that I can have that. The u is the red part, and then the dv is the part that's in blue. And the antiderivative itself, script is not any colors. Okay, so down here, I'm going to let my dv be the x cubed dx that remains. Everything hinges on the setup, kind of like in chapter 7, right? If I don't draw the picture right to start with, I'm usually going to end up in a mess later on. If I don't identify that I'm doing it with dy or dx in 7, I'm going to end up with a problem later on, right? It's the same thing here. I have to get the u and the dv right, or I'm going to end up with a problem later on. And usually you're going to be able to figure out that there's a problem because something's not going to work out right. So it's usually not something that you're going to be like, oh, I didn't realize there was a problem. You're going to know you made a problem spot, and you're going to have to go back and fix it. So what is the derivative, that is, what is du of the natural log of x? What's the derivative of natural log of x? Very good. 1 over x dx. Okay, just like in u substitution. So the u part looks and feels a lot like a u substitution step, right? I take the derivative of u, it's 1 over x dx. This other part, though, I'm going sort of back up, right? I'm moving from the dv up to v. All right, so moving up, what's the antiderivative of x cubed? Good. Uh-huh. And we won't need the plus c's for what we're doing. In general, we do have plus c, you're right. What we're doing right here won't need them, so we don't have to worry about putting them on. So that's good news too. Okay, everybody good so far? Okay, so what the formula said, I'll write it here at the top. It said that the integral of u dv equals u times v minus the integral of v du. Okay, so I don't know how you think. I am a very visual thinker. If I can see a pattern or I can see a process that I can always put things in the same spot, my brain goes towards patterns. So we put things in along this diagonal right here, correct? That's where we started, was along this diagonal. When I do my integration by parts step, I do things in a different pattern. I start by multiplying the u and the v together, okay? Well, that step doesn't require any antiderivatives. I just write it down multiplied, so it's a very lovely step. It's just the natural log of x, and it's times, in this case, x to the 4th over 4, u times v. And then I subtract the opposite diagonal as an antiderivative. So minus the integral of v, which is x to the 4th over 4, du, which is 1 over x dx. Okay, so I put things in along what I'll use my colors as identifications, along my black diagonal. I multiply these along the red circle, right, my red top circle, and I subtract the integral along the opposite or the blue diagonal. So you might be looking at that and saying, well, that looks terrible. It kind of does look terrible, but it's workable. I can work with it. I could not work with it the way it was before with the tools I had. I can work with it now. So what do I mean by that? Well, I can rewrite the first piece. I don't have to take its antiderivative or anything. So if you prefer, you can write the 1/4 here. I'll write my x to the 4th in front because then I won't have to use parentheses. So this is 1/4 x to the 4th natural log of x, or some version of it like that. It doesn't really matter, okay? This other piece, though, I need to take an antiderivative of it, and it looks like it's multiplication, but it's multiplication that I can simplify. How in the world can I simplify this? Well, the 1/4 can come to the front. I don't need to worry about it. What power do I really have of x?
X to the third.
X to the 3rd. I can take the derivative of that, antiderivative, of that, no problem. What's the antiderivative of x to the 3rd? X to the 4th over 4. We actually took it a minute ago, right? And then, like Piers mentioned before, we're going to do a plus c, but this plus c is going to show up here, okay, as I take my final antiderivative. So this is 1/4 x to the 4th natural log of x minus 1/4 times x to the 4th over 4 plus c. And the last thing I'll need to do then really is just to clean that up a tiny bit. And I can write this, if you prefer, you can write it as 1/16, or you can write it as x to the 4th over 16 plus your c. Okay, the point is that we want it to be in a place where it's workable, that I can do something with it. I want to do one more. And then I think we're going to stop there. It seems like a good spot to stop. Okay, definitely looks like a product, right? That's kind of a red flag thing for these. Not all of them are going to have that feature, but most do. Looks like a product, so a integration by parts is a good place to go. Remember, identify the u and the dv. And there are basically two pieces here, right? The dx is going to always go down at the dv spot, so that's a given. But there's two pieces here, and I have to figure out which one to let u be and which one to let dv be.
Well, isn't ex, its antiderivative is ex?
Yeah, e to the x is antiderivative and derivative is itself, right? It just goes back and forth. So the goal, remember for you, if possible, is that it gets easier. But if e to the x is what I let u be, it doesn't change. So it doesn't get any easier. So I don't want my e to the x to be u, because it doesn't get any simpler, whereas x cubed does. Yes? So my u will be the x cubed, and my dv will be e to the x. Yeah?
So I'll make the dv the simpler part of the equation then?
It's not necessarily the simpler part, but it's the part that I can take the antiderivative of as is. And that's kind of how this was described, although it sounded funny at the beginning, right? It's the most complicated part, like you just said, it's the complicated part that I can still take the antiderivative of. Yeah? I can still take the antiderivative. In fact, I could take the antiderivative of either of these pieces, but, right, step number 2 says, but if I can, I'd really like for you to be the thing that gets easier to take, as I take its derivative. And that is actually determining for me that that's x cubed in this case. Now, there's a caveat to this. We're about to hit it, but let's move forward and you'll see. What's the derivative of x cubed? Derivative.
Oh, the derivative.
3x squared, right? Okay, so I'm glad you did that because it's really easy. We're taking derivatives and antiderivatives within the same problem very close together. Be careful because it's really easy to do the wrong one in the wrong time, right? And this should have a dx on it. So the du is 3x squared dx. What is the antiderivative of e to the x dx? Just e to the x. Okay, so I rewrite this by multiplying across the top first. Okay, so that's x cubed e to the x in whichever order really that you wish, but I'll just put it in order from left to right, x cubed e to the x. And it's minus the integral along the opposite diagonal, which is 3x squared e to the x dx. What's going to happen, Braden? You have to do it again. By the way, I didn't pick on Braden. I could see that he knew what to do next. Why? What clued you into that?
They're multiplying each other.
It's still a product.
You have to do it 2 more times?
2 more times. Yeah, you do. It's still a product, right? It's 3x squared times e to the x. That's still a product. It's a smaller exponent on x, right? So I've made progress, but it's still a product. So I'm not done. So I'm going to minimize this and scoot it over a little bit because I need to keep going. So this was step 1. By the way, this piece now is done. I don't have to do anything with it. Agreed? It's not underneath an antiderivative, nothing like that. It just is what it is. It's part of the answer. It will continue on. It just comes along for the ride as we keep going, kind of like constant multipliers would. It's just going to stay there. It's the other piece that I have to deal with. So over here, I still have 2 pieces. So I still have to redefine a u, and then I'll get my du, and a v, and define my dv. What will my u be for this second piece? What will it be? 3x squared, the part that's going to get easier as I take its derivatives, right? And my dv will be still e to the x dx. All right, so what's the derivative of 3x squared? 6x dx. I'm kind of running myself out of space a little. Move this a little bit. And the antiderivative of e to the x is e to the x. Okay? So is everybody okay with that? Because I'm about to shift it down to give myself some space to work. This is my second step. So as mentioned before, this first piece stays the same right here. There is a negative still that I need to be careful of right here. It's a good place to make a mistake right there. There's a negative. I'm going to put a bracket here, and we'll make sure we distribute the negative before we're done. And I come back over here, and I need to multiply across the top. So I have 3x squared and e to the x now. So 3x squared e to the x minus the integral, and I use my other diagonal. So my other diagonal gives me 6x e to the x dx. Do you guys see now why Braden said I'm going to have to do it 2 times? It's still a product, right? Okay, before I go doing that, though, I really would like to make this a little bit nicer about the fact that there's a negative in front and distribute that negative through so that I don't end up with wrong signs. I'm constantly telling my children in algebra right now, check your signs, check your signs, check your signs, because it's so easy to lose them, right? Really it is. So x cubed e to the x, and this one will be minus 3x squared e to the x, and then it'll be plus the integral of 6x e to the x dx. This, again, is a product, like we've already said. But we're about to be able to deal with it, right? We really are. We're close to done. We need a u, and we need a dv. What will u be? 6x. What will the dv be? E to the x, again. So what is the derivative of 6x? 6dx. What's the antiderivative of e to the x? For now and forevermore, it's e to the x, right? So again, these pieces at the beginning get rewritten x cubed e to the x minus 3x squared e to the x. And then I need to do u times v. So that's plus 6x e to the x minus the integral. And now I need v to u right here. So there's a 6 and then an e to the x dx. But over here, there's no product. I do realize the 6 is being multiplied, but it's a constant multiplier, not a variable multiplier, right? Variables create products, not constants. So what's the antiderivative of 6e to the x? 6e to the x. And there's a negative just because there's a negative in front of this, right? So we have x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6, and its antiderivative is itself, e to the x, and then we need plus c. And here's the deal. We're not going to do it, but here's the deal. If I took the derivative of this, it'd be awful, first of all, right? It would be messy. But it would simplify to x cubed e to the x. Things would pair up, things would combine, things would cancel out, and it would clean up really nice and tight into x cubed e to the x, which feels a little bit counterintuitive. That's okay. But we'd have lots of product rules, right? Like I'd have to do the product rule of x cubed e to the x, and the product rule of 3x squared e to the x, and the product rule of 6x e to the x. This piece would be simple, right? And then the c would go away, and things would start to collapse, and we would get back to the x cubed e to the x. Okay, we'll stop there for today.